Hi, I'm Gal from Tel Aviv University, and this is joint work with Gil and Itay about tight bounds for the Zig-Zag product. We'll start with a quick recap of spectral graph theory and some notations. Having an undirected graph G, we can describe it using its adjacency matrix A. And if the graph is undirected, the matrix is symmetric. So we know it has n real eigenvalues, n being the number of vertices in the graph. And if the graph is d-regular, we know that lambda 1 equals d. This is called the trivial eigenvalue of the graph. And lambda n is greater or equal than minus d. And we have a quality called lambda of g, denoted lambda of g, which is the max absolute value of all the non-trivial eigenvalues of the graph. This is a number between 0 and d. And we can also normalize it by d and denote it omega of g. And this is now a number between 0 and 1. And it is well known that this number, the smaller it is, the better expander the graph is, meaning that small sets expand and also random walks converge faster and other qualities as well. We will refer to both omega and lambda as the expansion of the graph according to context. So we want this number to be as small as possible, but we also want the graph to be sparse, meaning we want the degree d to be as small as possible, which raises the question about the trade-off between the two, which was answered by the Alon-Bopana bound that tells us that lambda of g is at least 2 square root of d minus 1, minus a term that vanishes with the size of the graph. In terms of omega, this tells us that between 0 and 1, you know that you can't go below something that is roughly d to the minus half. With the Alon-Bopana bound in mind, we turn to review some of the known constructions of expanders. Graphs achieving the Alon-Bopana bound are called Ramanujan graphs, and these, for particular values of d, were constructed already in the 80s by Lubotsky, Phillips, and Sarnak, and by Margulis, using number theory and group theory constructions. We also have Friedman's theorem, which was later simplified by Bordenov, that tells us that a random d-regular graph is with high probability almost Ramanujan. And in addition, we have the Zig-Zag construction by Reingold, Vadan, and Wigderson, that is slightly worse in the parameters. It achieves order of d to the minus fourth and not d to the minus half. However, this construction is purely combinatorial, easier to understand. I will describe it in a minute. And we focus in this work on trying to improve either this construction or its analysis. So what is the Zig-Zag product? You start with a graph G, a large graph, and a small graph H, and we need the degree of each vertex to match the size of the small graph. In this instance, it is 4. And the zigzag of G and H is constructed as follows. First, you draw the large graph even larger. Then you replace every vertex in G by an instance of H. This isn't quite yet the zigzag product, but this object is called the replacement product, which we also handle in our work. And then you replace every edge in G by a corresponding length to walk in the graph H, and repeating this process for every edge, then removing all the edges of H as well, and repeating this process until we get a much more a larger and more complex graph, hopefully with good expansion properties. So what are the properties of the zigzag product? We first need to think what properties do we care about. So we think about the size of the graph, its degree denoted by uppercase D, and its expansion that the normalized expansion we denote by omega. So if we start with graphs G and H with corresponding parameters N, D, and C, and we denote their expansions by omega G and omega H, then the construction I just described produces a graph of size N times D. This is clear from viewing the construction, and also the degree is C squared. Note that it does not depend on the degree of the original large graph G. And from the original paper by Reingold, Vadan, and Wigderson, the spectral expansion of the zigzag product is upper bounded by, ignoring lower order terms, the sum of the spectral expansions. And under reasonable assumptions, the dominant term here is omega H, and it can be proved that this is O of C to the minus half, which clearly resembles the Alon-Bopana bound. However, note that the degree of the zigzag product is not C, but rather C squared, which achieves the degree to the minus fourth bound that we mentioned earlier. Now, before diving into our results and the analysis, I wish to suggest an experiment. First, we know that the value of omega of the zigzag product has to lie in this region between the lower bound, the Alon-Bopana lower bound, and the RVW upper bound I just mentioned. And I ask the following question. What if I fix a small graph H and I pick a deregular graph G at random from a standard distribution like the configuration model? What would the expansion of G zigzag H be? If you perform this experiment, what you'll notice is that the result is pretty consistent, somewhere in between, closer to the RVW bound. And we first ask the question, what is this number? What are we observing here? And the result I'm about to show you answers this question. And the answer is in the form of a lower bound for the spectral expansion of the zigzag product. Formally, our result is as follows. For every graph H, there is a number, ZH, that we can calculate, such that for every graph G, the spectral expansion of the zigzag product of G and H is lower bounded by this number. And also, this bound is tight, meaning that there exists a graph G such that lambda 2 of the zigzag product is upper bounded by this ZH. Now, as a corollary to this main result, we were able to show that omega, the normalized expansion of G zigzag H, is lower bounded by C to the minus half, meaning essentially that the original RVW upper bound is asymptotically tight. I will mention that we have similar analogous results for the replacement product, which we denote by R of H. Now, what is this value ZH? It is the minimum value of this function defined using the characteristic polynomial of the adjacency matrix of H squared. This function has the following looks, and by saying that I'm taking the minimal value of x, I just say that I lower bound this the value of this function. And for the corollary I just mentioned, we were able to prove that the value c to the 3 halves is always smaller than this number zh, and when normalized by the degree c squared, we reach the desired result. At this point, you may ask yourself, well, what does this function or this value, minimal value of zh, has to do with the zigzag product and the combinatorial construction I've just shown? This question has two answers. One for the lower bound using analytic combinatorics, which I will describe in the next couple of slides. And the second answer is an upper bound or construction using finite free probability theory. And what is most surprising in this work is the deep connection between the two fields, where two completely different techniques, one for proving lower bounds and the other for constructing a graph randomly, produced the exact same result, one for the lower bound and one for the upper bound. As an invitation to understanding our lower bound techniques, I will briefly describe the tools of analytic combinatorics. Assume we have a sequence of numbers we wish to calculate, denoted by AI, and I write down its formal generating function a of z. And assume also that the AKs grow in exponential rate, like beta to the k, times some sub-exponential factor f of k. And assume also that beta is the number we care about. We want to know in what exponential rate those objects grow. The main theorem of analytic combinatorics tells us a very surprising fact, that if you look at a of z not as a formal power series in the formal variable z, but rather a complex function in the complex variable z, we now look at this function and ask, in what region is this complex function analytic? And this region defines what is called the modulus of singularity, or the radius of convergence. And this notion from complex analysis tells us a very surprising fact about combinatorics, because beta, the number that we care about the exponential rate of the objects we count, is exactly 1 over this modulus of singularity. Now, what does this have to do with the zigzag product and spectral expansions? Well, if the numbers I care about are closed walks or cycles of length I in a graph, we know by using a very standard tool of the trace method, we know that this can be used to lower bound spectral expansion. What I just described tells us that it is enough to argue about the generating function of the objects we count. So in order to get to this generating function, we use the symbolic method, which we also overview in our paper, to give a symbolic recursive description of how closed walks in the graph look like. And this symbolic description leads to a functional equation of the generating function we care about. Now, the problem with that is that this functional equation is not solvable, meaning that we can't get an explicit expression for the generating function of the closed walks in the graph. However, a famous quote by Philippe Flageolet, one of the founders of analytic combinatorics, says the follows: if you can specify it, you can analyze it. If we were able to specify the symbolic description of the class, we will be able to analyze it. And recall that we don't necessarily need to know the exact form of the generating function. We only care about its modulus of singularity. And this is possible to do using tools from complex analysis. As I mentioned, the upper bound, the construction, was achieved by the use of tools from finite free probability theory. So how does free probability help us analyze the zigzag product? I will start by describing the adjacency matrix of the zigzag product using a product of 3 ND times ND matrices. This description was already shown in the original paper by Reingold, Vadan, and Vigdelson. And these matrices are the following. H tilde is the identity tensored with the adjacency matrix of H, meaning it's just a block matrix with the adjacency matrix of H on the diagonal. And G dot can be described as follows. So if I have two vertices U and V in the graph G, in the original graph of size n, and these are connected, and U views V as its ith neighbor and V views U as its jth neighbor. In this particular case, G dot, the matrix G dot, the rotation matrix of G, the edge rotation map of G is equals 1 in the entry Ui and Vj, and it is 0 everywhere else. Now, why is this helpful? Because it helps me describe how a random choice of G looks like, which is just taking a fixed G dot for any graph, which can be shown to just equal a matching of n times d, a matrix of n times d vertices, a perfect matching, and P is just a random permutation, a uniformly chosen random permutation. And this choice of G is what is known as the configuration model of the irregular graphs. And now tools of finite free probability enable us to say that lambda 2 is upper bounded by the maximal root of the free convolution of two polynomials, where one polynomial is depends on the graph H, it's just the characteristic polynomial of H squared, and the other polynomial is the characteristic polynomial of a fixed matching. And this is an extension of the works of Marcus Spillman and Srivastava that used similar techniques to prove the existence of Ramanujan graphs of every size. To recap what we've seen, we've shown that the zigzag product is quadratically far from being optimal, from matching the Alon-Bopanna bound. And we've also seen that lower bounds using analytic combinatorics and constructions using finite free probability actually match. And we also observe that both represent the behavior of a random choice of a graph. And I will mention that there are possible extensions for this work. Obviously, for other combinatorial constructions, we have shown the zigzag product and the replacement products, but this can be applied to other combinatorial constructions as well. And it can also be used to derive general lower bounds for different parameters of C and D, the degrees of both graphs. Thank you very much for listening, and feel free to reach out.